My name is Lourdes Agapito, and I'm a professor of 3D Vision at University College London. I'm really honoured to have been invited to talk to you about what I think has always been the most exciting and challenging problem in computer vision. And that's how do we learn representations about the world that are 3D aware? And how do we do that only from images or from videos that have been taken from a single camera? So I've been working in this area of learning 3D representations of the world for around 25 years now. So I hope to offer you a perspective of how important and pivotal machine learning has been for this field. So when we see this image, as humans, we get an instant sense of 3D understanding. Some of it is purely geometric. Perspective helps us to understand the layout of this busy market, and we can instantly tell what's close and what's far away. But a lot of what we understand is also via our prior knowledge. We know the rough shape, the colour, the texture and size of different fruits and vegetables. We could tell how far a person would have to reach to pick up some tomatoes, or understand how heavy a pumpkin would feel in our hands. There is so much prior knowledge here that it seems like a perfect task for a machine learning algorithm. However, when we look at the large computer vision datasets that have been collected for image recognition and detection, it turns out that they only have 2D annotations, such as class labels, masks, and key points, because these are relatively easy and cheap to annotate. But on the other hand, aligning images with accurate 3D shapes is extremely hard and expensive. Although some effort has happened in recent years to collect 3D datasets such as ScanNet or Matterport or ShapeNet, these are still very limited. And therefore, the easy way to go about this, which would be a fully supervised approach, is completely out of the question. But in fact, we have solved this problem of 3D reconstruction from weak annotations or directly from images without any 3D labels before. If we look back at old school geometric methods for 3D reconstruction, these are, in essence, weakly supervised or self-supervised methods. So one of the big successes in the area of geometric computer vision was structure from motion, where we take as input a collection of images, we extract some point features and establish correspondences. Then we estimate parameters of our 3D representation, which in this case are the 3D coordinates of the world points and the camera poses, such that when we project them back onto the image via perspective projection, they agree with our 2D observations. So we learn a 3D representation, but our loss is 2D. So no 3D annotations are needed in this case. Another example is multi-view stereo. Here our observations are the images themselves, and the problem we solve is, can we reconstruct a dense 3D mesh such that when we re-render our estimate back as images, our synthesized observations agree with our input images. This is also called analysis by synthesis. To do this, we essentially use a photometric loss to guide the estimation of the depth of each point. Then the intensity of corresponding points should be the same. No 3D annotations needed here either. For these two examples I've chosen, the inference of the parameters of the 3D representation is done via optimization. But the intuition here is that we could also use neural networks for the inference of our intermediate representation, which was represented in green here, given that our loss in this case is the photometric loss, which is a 2D loss only. So this now opens a world of options, these kind of models. Which representation do we use? Do we use discrete voxel representations, which can be processed nicely via 3D convolutions, or do we use unstructured point clouds or meshes that have an idea of connectivity, or do we use an implicit and continuous representation, such as a sine distance function? Even more exciting is the current trend of representing scenes via fully connected networks that stores values such as the occupancy probability for each point location in the scene. Another interesting question is, what image formation models do we use to re-render our observations? So we will use perspective to model how 3D points are mapped onto the images, but we can even model how light interacts with the geometry of the surface to form an image. In terms of observations, we can use key points, we can use masks, or just the images themselves, or either RGB or depth images. Now, when we come to what annotations we use, as we said before, we really prefer 2D weak annotations or self-supervised approaches. But so far we've talked about capturing a static world. In many cases, what we want to capture is also the dynamics. We want to learn 3D representations that can explain not just a single instant in time and captured just a unique single shape, but that they can capture any possible deformation and configuration of this shape. And this is the main topic of my research, is learning 3D deformable models that can explain how the shapes of objects evolve over time, or how they vary across a category of objects, and learning them from images. So this brings one more element to our 3D representation, which is shape deformation priors that encapsulate the variations of shapes and deformations across object categories. So typically, these are pre-trained from thousands of 3D scans. Some of these are parametric, like the face model, the 3D morphable models, or the body model, the simple body model that you can see here. But others are encapsulated in the weights of a neural network. Then at test time, the problem can be framed as, can we fit the parameters of these models to our current observations, where the observations are now images? So the question we really want to ask is, can we actually learn these priors from images directly without the need for this pre-training stage with 3D data? Why these scans, acquiring these 3D scans, even though it's just capturing 3D data and we don't need to associate them with any image annotations, it's still a very expensive task. So I'm now going to show you one example in which we learn a deformation prior purely from images. This is work from CVPR 2013, so fairly old now. Given a video sequence of a deforming object, the goal here is to reconstruct a dense per pixel model for every frame of the scene. So in terms of our observations, we take the original video and we track all the pixels in the image over the entire sequence. So our observations are the 2D point trajectories over time that you can see are being tracked here in this video. Now we want to reconstruct a model such that when we project the mesh back onto the image via the camera, we get our observations back. Or in other words, the 3D points that we've reconstructed must reproject back onto the tracks. But this is not enough. There would be an infinite number of possible shapes that could reproject onto the same measurements. We need to add a prior. And the prior in this case is that if we took all of the shapes from the entire sequence, they lie in a low-dimensional embedding. And we impose this by minimizing the trace mode. What we're doing is explaining all the frames in the sequence with as few components as possible. So K here is a lot smaller than the number of frames F. Essentially what we're saying is that the shape of each frame can be explained as a linear combination of some basis shapes, but where critically these shapes are unknown, these are actually the prior that we are estimating. We take all of these terms and we include a spatial smoothness prior to promote smooth surfaces, and then we run an optimization over the shapes and the camera poses. Our loss is 2D, the reprojection error, and our final scene representation is a low rank embedding that can explain all the frames in the sequence. So it's a much more compact representation than providing the reconstruction for each different frame individually. Here are some results on face reconstruction. So this was the very first dense, non-rigid 3D reconstruction method from monocular video sequences. So the great advantage of this method is that we can reconstruct any shape, since we're learning the low rank representation directly from 2D data. So here we're looking at surgery of the heart, so we can reconstruct the tissue of the heart, and we can also learn a prior of the deformations of the heart. So something else that we can do is that instead of using this reprojection loss, we can now use a photometric loss. We can look at consistency of the color for corresponding points over time, and we can reconstruct video of deforming objects. And the same thing happens here, that we can reconstruct different kinds of shape, given that our prior is actually agnostic to the kind of object that we are reconstructing. So this is nice when we're looking at objects for which we don't have enough training data to pre-train a prior. But in many cases, such as the case of the human face, these models exist and we can use them for tracking. So the idea is the same. We estimate the model parameters such that when we re-synthesize the images, we get back the same observations. And in this case, this model-based face tracking, what are the parameters in this case? The camera pose, the overall shape of the face, the colors of the texture, the illumination, and the facial expression. So this modeling works incredibly well. So when we synthesize the observations using our estimated model, shown in yellow here, the errors are tiny when we compare to the original image. So the fact that we are modeling the face so accurately in 3D means that we can then later edit these parameters that we've estimated, and we can re-synthesize new movements for the face. So this is something that we're using in a startup company called Synthesia. I'm going to show you one of our most important demonstrations of our technology.
Malaria isn't just any disease. It's the deadliest disease there's ever been.
Se dice que ha matado más de la mitad de la población que ha existido. وما زالت تقتل طفلا كل دقيقتين. Mais nous pouvons y mettre fin. Nous savons comment, nous en avons la possibilité. हमें और अधिक कार्रवाई की जरूरत है.
我们需要让世界领导人关注. Hivyo tunazindua kampeni ya sauti. malaria.
Speak up and say, malaria must die. One voice can be powerful, but all of our voices together, then they will have to listen. Malaria must die, so millions can live.
Of course, Beckham doesn't speak any of those languages, but what we can do is track other actors speaking their languages and then transfer the lip motion. This works really nicely because we are tracking the faces in 3D. So we've seen how embedding 3D shape priors into 3D reconstruction of deformable objects works really well. We're now going to move on to how we represent full scenes. A representation that has been very successful recently is to represent the scene at the level of objects, or object-aware representations, where we don't just represent the scene as a bunch of 3D points, but we also attach them semantic labels. So the trick here is to combine 3D reconstruction with 2D detectors and 2D semantic masks, and to transfer these labels onto the 3D model in a consistent manner over time. So here we can see that while we are reconstructing, we are also associating semantic labels with the different objects that are segmented and can even be tracked with their motion as independent from the rest of the scene. So how can we move to the example on the right, where we reconstruct each object as a complete shape, even when what we have are partial observations? Can we actually do this just from images, from a set of input images? So here, the key is to use a pre-learned shape prior for each object category. And in this case, we're taking advantage of a very novel way to represent shapes in a very compact way. So in 2019, the same idea was developed in parallel by a few different groups to use a fully connected network as a continuous shape representation. The idea is that we feed a 3D point location to the network, and it returns a value that's related to the geometry of the shape. In the case of occupancy networks, the network learns a classifier to whether or not the points are on the surface. In the case of deep SEF, the network returns the distance to the closest point on the surface. And these representations can be trained from 3D data. They're continuous representations, so they're not governed by any discretization that we must decide in advance. So looking more closely at deep SEF, its architecture is an autoencoder. At training time, the weights of the decoder are learned, but also an embedding of latent codes where each training shape will be assigned a different code in the embedding. At test time, we take an incomplete point cloud as input, and the weights of the decoder are fixed. And then an optimization is carried out to estimate the code that, when decoded through the prior, leads to the shape that most agrees with the current 3D observations. So the question we asked ourselves was, could we estimate these shape code vectors just from images without needing any 3D data at inference time? So we use DeepSDF as the pre-trained 3D shape prior. And here we can see how different codes are decoded to represent either a dense representation or a point cloud representation. And then we follow an analysis by synthesis optimization. So given our current estimates for the object pose and the shape code, we decode the shape using the pre-trained DeepSDF decoder, and we synthesize our new observations. So our losses are 2D, a photometric consistency loss, a silhouette loss, and a key point loss. So here are some results on a real-world data set. This is the Redwood data set. Our reconstruction is in the last column. So we can reconstruct from as few as 2 or 3 images, but of course the larger the sequence, the better the estimates will be. So this is work in collaboration with Facebook Reality Labs and the University of Adelaide that appeared last year in CVPRW. Here are some results on larger scenes with multiple objects from ScanNet, which is a large-scale real-world data set. You can see how each of the objects is being detected and has been reconstructed, and we have complete representations, complete shapes for the objects, despite the fact that our observations are incomplete. And this is because we're using the shape priors to basically complete the parts of the shape that we don't observe. So this same reconstruction strategy can also be used within a SLAM system to operate in real time and to reconstruct large real-world data sets like the Kitty data set. So this is recent work from my lab. And here we can see some examples of the reconstructions at the level of objects that we can obtain for real-world images that come from the Kitty data set. And here is the system in operation. In this case, we do use a few LiDAR points as information. And you can see that we can track the position of the camera in real time, and we can reconstruct the scene at the level of objects, and we can reconstruct a full 3D map where we can represent the objects as points in our map. So I could not give a talk in 2021 without talking about the paper that shook the 3D vision community in 2020. This paper is NERF, Neural Radiance Fields for View Synthesis. So this paper takes the idea of using a fully connected neural network as a continuous representation of a 3D scene further than what we've seen already in DSDF, and showed how this can be trained from images only. Now, there's no need for 3D data at training time like DSDF. The idea in some ways is quite simple. Take a set of input images with known camera pose, and then learn the weights of a network that's trained to re-render the training views. At test time, this pre-trained network can be used to render new views from unseen points. It works amazingly well. These were the results that really got everyone hooked. And the reason why it works so well is that it uses multi-view photoconsistency as the loss, and the internal representation is 3D aware. So NERV represents the scene as a network that takes in the XYZ location of a point and the viewing direction from which it is observed, represented here by the ray. The output of the network is the color of that point and its density, represented as sigma. Volume rendering is then used to infer the radiance of each pixel. Volume rendering takes all of the point samples along the ray and integrates their colors weighted by their density. The loss is the usual loss we have seen before. Synthesized views are compared with the input views that are the ground truth representation of the radiance. So this fits exactly with the analysis by synthesis model that we saw before for multi-view stereo, for instance. But now the 3D scene is represented with the weights of a neural network instead of a 3D mesh or a set of boxes. And this is an incredibly compact representation. Now, as cool as NERF is, an issue that it has to be trained from scratch for every new scene. It overfits to the scene and cannot generalize to new observations. So what if instead we want to model the variations of shape across a category, as we can see here, and still be able to train it from just 2D images? So this is some recent work from my lab that goes in that direction. So what we have learned before through this talk is that what we need to learn is a shape embedding or a prior that encapsulates the variations of the shape across the category. And we need to learn that at the same time as we learn the 3D representation. We take inspiration from DeepSDF and represent the scene using an autodecoder that learns to infer RGB and density for each point, but also takes in two latent codes in this case, one to represent the shape and the other to represent the texture. In this way, we can disentangle both latent spaces during training, and at test time, we can edit shape and texture codes independently. The rest of the pipeline is similar to NERF. We also use volume rendering to resynthesize the training images. At test time or inference time, we're given a new image of an unseen object from an unknown viewpoint. The network parameters are fixed, and what we optimize are the model parameters, which in this case are the shape and the texture codes specific to this particular image, as well as the camera pose. And all of those will be the ones that best fit our reference image. And of course, we use a photo consistency loss. So here we're going to see a video on the top row. You can see the input images or the reference images, and on the bottom row at the moment you can see the initialization overlaid with the renderings throughout the optimization steps. So as the test time optimization is happening, we can see that our estimates of the shape and the pose of the camera and the texture code are all converging towards being able to render back the reference images. And now, of course, what we can do is that we can synthesize new unseen views for those objects. So we can vary the camera pose, and we can synthesize views that we haven't seen before. But because we have disentangled texture and shape, we can also synthesize new textures. So here we fix the shape and we change the texture of the object. And we can do it the other way. We can fix the texture and we can edit the shape. And something interesting we can also do is that we can perform single view reconstruction. Given a single image, we can reconstruct a 3D colored mesh that represents the shape of the object, and it's encapsulated in the neural network. So what is next in 3D computer vision? So for the last year, the community has been incredibly busy with extensions of neural radix rules. So some methods have focused on generalization, like ours, to represent object categories, or to generalize to new scenes from just 2 or 3 input images. Others have focused on extending NERF to deal with definitions of faces or bodies or dynamic scenes. Others have focused on disentangling geometry, lighting, and material properties so that they can be used further for relighting scenes. And finally, there's also an exciting work in the direction of training neural network representations on the fly in real time. This is done from depth images currently in the work shown there. But really, what we have been avoiding all the way is what can we actually learn useful representations. So we've been very focused on being able to learn representations of the 3D world just from the available training data that we have, which is 2D training data exclusively. But are these representations really useful to a robot, for instance, that has to interact with humans? So to be able to do that, we need a big step change. We need to be able to learn in real time. So we need to be able to learn about the current scene on the fly. So perhaps have some pre-trained models that have some certain priors about geometry, but then specifically learn the scene where the robot is going to be operating on the fly. We also must be able to learn from very, very few examples. We must be able to learn other useful scene properties about objects. For example, what are the grasping points? What are the affordances of each of the objects? I think we do have a very good framework with these neural representations where we can associate different outputs to the values of the network. We should also be able to learn about safety. How does the robot go about this scene in a safe way when interacting with humans? This is a huge area that we really haven't even begun to scratch the surface of. And then, if we can actually reconstruct the shape and the poses or the facial expressions of humans, can we even predict their intentions? Can we anticipate what they're going to do so that we can adapt what the robot is going to do according to those intentions? So I'd like to finish with thank you to my team and to all of the collaborators and the funding bodies that have supported this research. Thank you.
Thank you, Lourdes, for the very nice talk. I really enjoyed learning about your varied work. About how do we learn from just having 2D data, say video or images, without needing to have 3D data to actually have a representation, to get a representation of the 3D world. Let me start by saying that I really also like the fact that in your talk you covered a bit of simple background for 3D reconstruction and how the optimization problem and some of the challenges, one of which is 3D representation. And we do have a question from the audience that asks, in your opinion, what are some of the challenges that you have faced when you were looking at 3D representation?
Yeah, thank you, and thanks very much, Angel, for the introduction and for the questions. So the challenges that we faced in terms of building 3D representations is that they're really my interest has always been to have representations of the world that don't just explain the geometry at a single instance. So to explain the geometry of let's say, of a rigid scene, but to try to understand how that's evolving over time, and to really embed the dynamics into the representation as well. So that's always been the main challenge, because we need to learn that from 2D observations only, as we've seen before. So to be able to encapsulate the way in which surfaces are deforming, or to be able to encapsulate the way in which let's say, cars are moving in a busy street, we need to not just have a representation of the actual geometry, but to also incorporate some priors about how we expect those surfaces to deform. How do we expect those objects to move? And in many ways, it's important that we can. So we're learning that from the images that we're perceiving. We're learning that from the videos, and it's important that we have sufficient information so that we can encapsulate all the different modes of deformation, and that's always the challenge. We need to be distilling what's important and represent that in the 3D representation. So this is why often when we can restrict these models to a single object category, then they can become very maybe easier to train and much more useful. For instance, if you think about the case of the faces. So we've got so much data, we've got so many videos and so much, I mean, even 3D data of faces deforming. Therefore, in that case, we can really distill the deformations and create a prior about how do we expect things to deform. So it really is about what I think is the main challenge is to be able to, let's say, build an internal model that allows us to simulate any changes that might happen to the geometry and the appearance of the objects. And of course, to do that in a way that we are using as little 3D training information as possible.
Yeah, I think that's a great point. And maybe I should move back a bit because maybe I jumped forward a bit to a very specific question. It really is very interesting to hear how much we can infer from about the 3D structure of the world now, and especially like what you mentioned about the representation, the need to not just capture static snapshots of what the geometry of something looks like at one point in time, but some representation that allows us to move forward. And I believe that is a very important message. But Lourdes, I wanted to, there is a question we wanted to ask all the speakers, which is that if you could share with us a key message from your talk, one message that you would like the audience to remember going forward, would it be just about the presentation, or would it be some other message?
Yeah, I think I think for me the message is that we've actually moved forward quite a lot in terms of capturing 3D geometry, 3D appearance, how that varies, let's say, when objects are deforming. But I think it's what I said towards the end of my talk. We need to make these representations. We need to make them useful. We need to make them useful so that, for instance, autonomous agents can actually interact with the environment. And I think that something that we're not doing just yet is make these representations so embody them in let's say robots that are interacting with humans and that are interacting with the real world. I mean, of course, there is a lot of work in the robotics community going in this direction, but I think that we're really not nowhere near really just robots being able to kind of coexist and interact with humans. And I think that that's partly because for instance, we're not learning much about the physics of the world. So this is something that we're not necessarily incorporating into our priors. We're also not learning from action. So if we can predict what might happen next, if we can predict how the geometry is going to change, how the appearance is going to change, I mean, that's a very useful thing to have if we want to go into this perception, prediction, and action loop that would be so useful. And I think that that requires also real time inference, and it requires real time building of 3D representations. And again, this is something that there's a lot of work in the community in real time 3D computer vision. There are SLAM methods that can reconstruct the world in real time. So I've demonstrated some of these methods in my talk. But there's still probably not enough work. actually reconstruct the shape and the poses or the facial expressions of humans, can we even predict their intentions? Can we anticipate what they're going to do so that we can adapt what the robot is going to do according to those intentions? So I'd like to finish with thank you to my team and to all of the collaborators and the funding bodies that have supported this research. Thank you.
Thank you, Lourdes, for the very nice talk. I really enjoyed learning about your varied work. About how do we learn from just having 2D data, say video or images, without needing to have 3D data to actually have a representation, to get a representation of the 3D world. Let me start by saying that I really also like the fact that in your talk you covered a bit of simple background for 3D reconstruction and how it's an optimization problem and some of the challenges, one of which is 3D representation. And we do have a question from the audience that asks, in your opinion, what are some of the challenges that you have faced when you were looking at 3D representation?
Yeah, thank you, and thanks very much, Angel, for the introduction and for the questions. So the challenges that we faced in terms of building 3D representations is that they're really my interest has always been to have representations of the world that don't just explain the geometry at a single instance. So to explain the geometry of let's say of a rigid scene, but to try to understand how that's evolving over time, and to really embed the dynamics into the representation as well. So that's always been the main challenge, because we need to learn that from 2D observations only, as we've seen before. So to be able to encapsulate the way in which surfaces are deforming, or to be able to encapsulate the way in which let's say cars are moving in a busy street, we need to not just have a representation of the actual geometry, but to also incorporate some priors about how we expect those surfaces to deform. How do we expect those objects to move? And in many ways, it's important that we can. So we're learning that from the images that we're perceiving. We're learning that from the videos, and it's important that we have sufficient information so that we can encapsulate all the different modes of deformation, and that's always the challenge. We need to be distilling what's important and represent that in the 3D representation. So this is why often when we can restrict these models to a single object category, then they can become very maybe easier to train and much more useful. For instance, if you think about the case of the faces, so we've got so much data, we've got so many videos and so much, even 3D data of faces deforming. Therefore, in that case, we can really distill the deformations and create a prior about how do we expect things to deform. So it really is about what I think is the main challenge is to be able to, let's say, build an internal model that allows us to simulate any changes that might happen to the geometry and the appearance of the objects. And of course, to do that in a way that we are using as little 3D training information as possible.
Yes, I think that's a great point. And maybe I should move back a bit because then maybe I jump forward a bit to a very specific question. It really is very interesting to hear how much we can infer from about the 3D structure of the world now, and especially like what you mentioned about the representation, the need to not just capture static snapshots of what the geometry of something looks like at one point in time, but some representation that allows us to move forward. And I believe that is a very important message. But Lourdes, I wanted to, there is a question we wanted to ask all the speakers, which is that if you could share with us a key message from your talk, one message that you would like the audience to remember going forward, would it be this about the presentation, or would it be some other message?
Yeah, I think I think for me the message is that we've actually moved forward quite a lot in terms of capturing 3D geometry, 3D appearance, how that varies, let's say, when objects are deforming. But I think it's what I said towards the end of my talk. We need to make these representations. We need to make them useful. We need to make them useful so that, for instance, autonomous agents can actually interact with the environment. And I think that something that we're not doing just yet is make these representations, so embody them in let's say robots that are interacting with humans and that are interacting with the real world. I mean, of course, there is a lot of work in the robotics community going in this direction, but I think that we're really not nowhere near really just robots being able to kind of coexist and interact with humans. And I think that that's partly because for instance, we're not learning much about the physics of the world. So this is something that we're not necessarily incorporating into our priors. We're also not learning from action. So if we can predict what might happen next, if we can predict how the geometry is going to change, how the appearance is going to change, I mean, that's a very useful thing to have if we want to go into this perception, prediction, and action loop that would be so useful. And I think that that requires also real-time inference, and it requires real-time building of 3D representations. And again, this is something that there's a lot of work in the community in real-time 3D computer vision. There are SLAM methods that can reconstruct the world in real time. So I've demonstrated some of these methods in my talk. But there's still probably not enough work in this direction of being able to really work in real time, so that we can have agents that are actually interacting with the world, so that we can learn also by how things move when we push them around. These things we're still not incorporating into our models, and it's important that we start doing this. And I see that at the moment, we're working hard on in two directions. One is this direction of synthesis. I think we've been very successful in this, right? So being able to create a 3D representation so that we can then synthesize new views, so that we can synthesize, the face saying something different. So, maybe sometimes we call this computational photography. Can we create and synthesize new images, right? And we've shown that having 3D representations of the world is extremely useful for that task. And we can synthesize. We can synthesize very well. And I think that the synthesis part is something that still needs a lot of work. But we kind of moved on quite far in that direction. But when we get to more physical interaction with the world and how useful having a 3D representation might be for autonomous agents to interact with the world, that's really where I think we need to do a lot more work.
Yeah. And thank you for the answer, and I completely agree that when you first started to talk about the usefulness of the representation, for me it's already like, oh yes, as you pointed out, we can already synthesize, and that's also very useful. But I guess your point is that we need to go beyond just being able to, say, mimic the appearance of, again, something static maybe, and even just different views, but to actually have additional information which maybe go beyond, I would say maybe it's going beyond the 3D geometry when you talk about the physics of something. And, this kind of information, which is very, very important. And to me, it's extremely interesting and exciting because, when we talk, I work with language and 3D, and when people talk about objects, it's not just the fact that it's maybe spherical, but also maybe it's soft. And if you touch it, it'll be form. How does the object change as you interact with it? So I think that's very, very exciting. And you also mentioned that when you feel that one thing that's important is to move towards this embodied setting where the robots can maybe sorry, that's a good example. But you mentioned that it's very important for the robot to be able to, say, interact with the object, potentially also learn from other people interacting. Can you give us a bit more of your thoughts on that?
Yeah, so I was recently involved in a 5-year research project. It was a collaborative project between a few different institutions and industry. It was a European project, and where we were designed a new robot. One of the teams completely built a new robot that was going to be working in a very complex environment, in an industrial environment, in an industrial warehouse, and was going to be working alongside humans. And here what we realized is that if a robot is going to be performing some tasks alongside humans, it obviously needs to have a 3D representation of its surrounding, but it also needs to have a way to anticipate what the humans might do, and to anticipate what's coming next. So the idea here is that this robot was going to help a human in some tasks without receiving commands, but by observing what was happening and being able to anticipate what was going to come next and not have to be told, pass me a certain tool. It was a maintenance task, pass me the hammer. So we didn't want that to happen. We didn't want the language to be used in a command way, but for the language to be used as an understanding of the robot, of here's my internal 3D representation of what's happening right now, and here is let's say a kind of high-level description of where we are in this task, and this is what I anticipate might happen next, and therefore I can already anticipate and offer help before I'm asked to offer help. So it's extremely complex. This project was extremely complex, but we saw how important it was at every time to have a 3D representation of the world, but also to combine it, as you said before, combine it with language, combine it with the objects we need to know about their affordances. So it really isn't just about the 3D geometry or the 3D appearance. It really is about the purpose of things, and it's about it really is about interpreting actions and what might happen next, and being able to carry out these predictions.
So the example you gave is actually going far beyond, I think, just predicting the 3D structure. It's actually also needing to have some understanding of like the goals of the other person that is working with. So that's I think very, very exciting and exciting work. Maybe we should move on to a question from the audience. So there are some questions about your work on the code nerve, and I guess there's a couple of questions. So one is that in your work there you have disentangled, like say, the shape and the texture information. And one question is, how do you ensure that these things are disentangled? And a related question is also like, once you have like this kind of latent space that may be a bit disentangled, is it possible to actually edit in this space so that you can create variations of this 3D object, so that you could say change, given an input chair, you can change the chair to the same chair, but maybe the original had the arms and now without.
Yeah, so the first question was about disentanglement,
Yes.
and I didn't go into details. The way in which we disentangle is it's in the architecture of the multi-layer perceptron, the MLP, that we're using to predict. So given an XYZ position and the viewing direction, we're predicting the RGB color and the density of that point. And so what we noticed is that the RGB, so when we're predicting the density, we don't really need to have the texture information. So the texture code doesn't really play a role in predicting the density. It's only really the shape code that plays a role in predicting the density. Whereas, both the texture code or the appearance code and the shape code, they both influence the RGB color, right? So that's the way in which we disentangle the two parts. Only the shape contributes to the density, and that's how we disentangle these two things. Also something that can be useful is that if we do have labels and knowledge, if we know that we have several images of exactly the same car with different textures, with different colors, then we could incorporate that into the learning as well. So it also, if we know that happens and in our data, then we can exploit that information as well. We don't. We haven't explicitly done this in our training, but we could if we have that information about the data. So the second question was about editing. The answer is yes. We can use these codes for editing and synthesizing new shapes and synthesizing new textures. And in fact, one thing we can do, I didn't show a video of this, is that we can interpolate between two different shape codes, or we can interpolate between two different textures, for instance. So we can navigate this latent space, and we can generate new unseen textures and shapes. So something that I think is quite important in this case is to realize that this method requires this test time optimization. So at test time, you're giving a new image of an unseen object in an unseen view as well, a viewpoint as well. So you're giving a new image of an unseen object, and you run a test time optimization to optimize, to estimate the code and the shape code and the texture code that corresponds to that particular image. So, for instance, for the interpolation task that we were talking about before, we could have a picture of one chair and then a picture of another chair. We could at test time estimate the codes corresponding to those two chairs, and then we could interpolate between those two. So we could potentially say, have a chair with armrests and another one without, and then we can sort of run interpolations between those two. So this is I think one of the most powerful ideas about representing shapes using these priors that live in a latent space. It's just the idea that later you can use this for editing and synthesizing new objects.
That I think is really great. It's really, I think, illustrates the importance of representation, and like the representation maybe doesn't always have to be interpretable by us, but can still be very useful, like in this latent space where you can, maybe it's not 100% interpretable, but you can still manipulate and change it. And I think it brings up, has a lot of power. One thing I wanted to ask was that you talk a lot about like this, the idea of having shaped priors, and I think you touched on this a little bit in your talk about, sometimes it can be also kind of challenging, right? Because especially when you want shape priors that potentially can generalize across shapes. And I wanted to ask, do you think that we have other challenges, and what are they? And is there some, what else do we need to incorporate, let's say, into this latent space?
Yeah, so I think I think that incorporating the variations of shape is important. There are also even, often, so something that's very useful is to have to have priors that are almost more loose. Can we actually maybe rather than learning priors on a category by category basis, which means that then at inference time we need to have some detectors that will, and we need to really join this up with recognition, right? So we need to have detectors that tell us this is a chair, this is a cup, and that's a. I mean, I think that's a very useful way to go about scene understanding, to combine the really powerful 2D detectors and 2D masks that we have, all the semantic information that we can extract just from 2D data, because we've been so computer vision has kind of almost solved that problem of having tons and tons of 2D images with 2D annotations, and being able to provide semantic masks, being able to provide detectors, localize objects in images. It's very useful. Now the problem is that if we then we need to we can only work with whatever categories we can detect, right? And maybe there's a lot of stuff in the background that we're not reconstructing, we don't care about. So we also need to incorporate, let's say, priors about the world that are telling us about maybe more loose information, loose priors that tell us about the fact that we expect surfaces to be smooth, that we expect them to be continuous, or if we're in the outside world, maybe if we're outdoors, then that's not always the case. If we're looking at a tree, then from the distance, yes, we might think yes, it is kind of a smooth surface. As we get closer, there's a lot of high frequency details in the geometry, right? So I think that being able to combine these low level priors with high level priors, having priors at different levels of understanding, it is a very useful thing, and something that some groups are starting to look in that direction, but not there's still a lot of work to do. Something else is that there's still, I think there is still I've said all along that what I want is to reconstruct 3D priors and reconstruct the 3D world from the observations only, right? So only from 2D data. But there are there's more signals in the world that we could potentially use, right? So maybe starting to think about how if we touched an object and how does it actually deform when we apply some force onto it? Can we actually use those priors as well to build these 3D representations? Can we, I said before, can we incorporate maybe physical priors? That's a very important topic, I think, that we need to continue working on.
Yeah, I completely agree. Completely agree. I guess there are some other questions from the audience. One that's a bit, just one question about the facial animation that you've shown, and it's pretty, it's pretty impressive. And I think part of that goes is due to having a good understanding of how the face works and having a good prior there. And so there's a question from the audience. The audience is saying, the demo is very, very impressive, but in your opinion, is face synthesis largely solved at this time? And if not, what are the remaining challenges?
Well, no, it's definitely not solved. There's a lot more work to do. So one of the important challenges in synthetic media, or synthesizing, if we're still talking about faces, is so at the moment we're kind of able to get to get a face to let's say say something new, right? So we can even so I haven't actually shown this, but we can even go from text to a synthesized video. So we can write down what we want the person to say, and we can go from text to audio, and then from audio to video. But something that is still a very hard problem is, for instance, to add expression and to add emotion. How do we say, well, we want the avatar, we want the person to say these words, but we want the emphasis so we emphasize it with a specific expression or even with body language. How do we add that to the synthesized video? How do we drive it not just with the content of what's being said, but also with the emotion, with the body language? That's still a very hard thing to do. As is, for instance, to go to the full body, for instance, rather than just the face. These are challenges that we're currently working on. And the other challenge is also to be able to use as little training data and as few images as possible to synthesize the new person. So in the video you saw before, when we were resynthesizing a new video for David Beckham, we need to have some video for training and for training the 3D model and for reconstructing the 3D model and for learning what are the dynamics of the face in that particular case, and then we can resynthesize again. But of course, in some cases we don't have maybe 10 minutes of video or 5 minutes of video. We just have a few different photos, and can we animate just from photos only? And there's a lot of work in the computer vision community and the graphics community in this direction at the moment, which is really exciting. How do we animate single photos, for instance, right? But there, it's a question of can we preserve the identity of the person? Can we really make the person move as that person would actually move, or because we've trained on other people, can we really generalize to a new person? So I think these questions about generalization, using a small amount of training data, and being able to edit, give more editing handles if you want, like, can we edit the expression? Can we edit the emotion? Can we edit the body motion, etc.? It's a very exciting field.
It's great to hear that there are still a lot of challenges, and I guess from your answer, what I will say is that we're not quite ready to replace all the actors yet. they are still needed.
Not yet. No. Something else that's missing at the moment is, yes, we can synthesize a person in speech, but what if that person picks up an object and starts interacting with an object? If we want to synthesize full scenes, dynamic scenes in action, it's almost impossible, really. Yeah. That's the big challenge.
So I think we're getting close to the end of the session, and I think here's a nice question from the audience as a last question is so they really enjoyed your discussion of the open challenges and how we could unlock new applications. And what we would like to know is, what are the key advances you would like to see from this community, from ICLR, to help solve some of these challenges that you're facing?
So I think I briefly mentioned before, to build these representations, we need to. So, okay, we have actually. So with this idea of NERF, of deep SDF, and other methods, proposed by other groups that encapsulate the 3D representation using a neural network, that's a really, really good basis, I think, for the future to move on. So this idea that we're using a network to represent 3D properties of the world. I think it's a really advanced way of representing the world, and I think that what the kind of challenges that I would like to see is how can we so at the moment, for instance, with NERF they learn RGB, the RGB color and the density. Can we actually start learning even more properties? Can we start predicting, for instance, a semantic label for a point? Can we predict, which part of the object does it belong to? If it's something that's going to be grasped by a robot, is this point a point from which it can be grasped or not? So I think that this is a very nice way to learn representations of the world. But for me, I think what I would like to see is more effort in how do we incorporate more supervision signal that doesn't require annotations to actually learn these representations, right? So we've seen that if you represent the 3D world and then you re-render it and then look for agreement with your images, we can train without 3D labels. But what about affordances of objects? What are the, let's say, 3 supervision signals that are there in the world that we could capture to learn about the 3D world and to learn maybe more useful priors. And I think this is where maybe in computer vision we're so used to just looking at images, right? I think this is where different communities need to come together. The NLP community through understanding how images and language connect together. As I said before, physics, robotics. I think it's building these representation learning that is kind of informed by all these different communities. In some ways, we seem to be working sometimes in slight isolation. So this is a perfect conference for people who are working in representation learning to come together and share the way that we go about learning representations, and in a way that it's useful for everyone, not just for the graphics community for synthesis, or for the vision community for associating useful labels with images, or the robotics community. Can we all come together and I think for me that's the really important thing. Is what other signals are there in the world that are they're cheap signals that we could exploit and push into the learning.
Thank you, Lourdes, again for the very nice talk and for taking the time to answer the questions. I think that's a very nice closing sentiment. The fact that representations are really super important, and it's great to be able to learn them and represent them in neural networks. And also, we really should be looking at these ways of getting cheap supervision. So I think those are great messages. And and I think we are over time. So thank you again, Lourdes, for your time and for your talk. And I would like to also thank the audience. Thanks to everybody who submitted and asked questions, and thank everybody for joining us for this session.
Thank you very much.